Software performance for embedded computing takes on a very different meaning than it does in typical IT applications. Many embedded systems must meet deadlines to ensure they operate correctly. Worst case execution time, or WCET, is an important metric that helps us determine whether our embedded system will meet its deadlines. Embedded software performance is a critical aspect of embedded system design. We need to understand the performance of the software modules in detail. We need to understand their real-time behavior, not just typical behavior. And we need to do this on complex platforms that include caches, complex memory systems, and pipelined architectures. Program performance is not the same as CPU performance. For example, the clock rate of a CPU tells us only in the most general terms the performance of our particular program. The pipeline and the cache are windows into the program, and they both affect the execution time of the program. In general, though, we need to look at the flow of execution of the program and analyze the entire program in order to determine the parameters of importance to embedded system design. Program performance varies with several aspects. For example, different types of input data, whether that be different values or different amounts of data, can result in execution paths of different lengths through different parts of the program. Cache effects are very important to understand in embedded system design. Instruction level performance variations are caused by things like pipeline interlocks and varying fetch times. We can measure program performance using different metrics. Average case execution time is typically used in IT applications. That's useful, but it's insufficient for embedded systems. Worst case execution time, or WCET, gives us the longest execution time for any set of inputs. We use WCET to help us determine whether the embedded system will meet its deadlines. In some cases, we may be also interested in best case execution time due to the fact that interactions at the task level can mean that best cases cause certain unusual conditions to occur. We can measure program performance in several different ways. We can simulate the execution of the CPU. This has the added benefit of making the CPU state visible so we can better understand why the program execution takes the amount of time that it does. We can use a timer to measure the execution on a real CPU. This requires modifying the program to control the timer. We can also use a logic analyzer or other external equipment to measure performance, but this requires that we can generate events on the pins of the processor that we can see using our equipment. Program performance comes from several different elements. The basic formula for program execution time is that it is a combination of program path and instruction timing. That is, what path of execution we follow through the program and the amount of time that each operation on that path takes. Solving these problems independently helps us simplify analysis. If we have a simple CPU, it's relatively easy to cleanly separate the program path and the instruction timing. For more advanced CPUs, the interactions between the two are a little bit stronger. Accurate performance analysis requires assembly or binary code and the execution platform. We can estimate certain aspects of performance using higher level, more abstract models, but to get very accurate analysis, we require detailed knowledge of both the software and the hardware. Even a simple program has several different paths through it. This example of code has 8 different execution paths for its 3 different variables that are used in the if statements. So you can see that for various combinations of A, B, and C, different statements and different combinations of statements are executed. So if we execute the program using only one set of inputs, we may never see the execution of another piece of code. And if that piece of code takes longer, we may underestimate the execution time. Loops also introduce challenges. Here's a simple loop. We start execution with the setup. We then execute iterations of the loop. And finally, we decide to exit the loop. We need to understand the execution time not only of the blocks in isolation, but the interactions between their components in the cache and in the pipeline. If we have conditionals inside the loop body, we have an extra level of complexity. In this case, we compute a function only when certain data values are present. That means that the number of times that the assignment F is executed depends upon the data. We also need to understand how long each instruction for a given operation takes. In modern processors, different instructions can take different amounts of time. We may have multi-cycle instructions. For instance, in the ARM processor, we can perform an operation on several registers. Memory operations often require longer and may take varying amounts of time depending on the states of the memory system. Furthermore, the execution time of instructions are not interdependent. Pipeline interlocks and cache effects mean that the execution time of one instruction depends upon the instructions around it. Execution times can also vary with operand value. For example, floating point operations may take a longer amount of time, in particular division and transcendental functions. We may also have some multi-cycle integer operations. Caches are an important source of timing variations in embedded systems. Here's a simple loop in a cache in which we have 4 words per line in the cache. The first access to a cache line during the execution of the loop causes a miss and a prefetch that fills in not only the word that we need, but also later words. Prefetching is an important aspect of computer system performance. Later accesses to that line can result in cache hits because we've prefetched the data. But that's only the case if that data has not been replaced by other data due to other operations that intervene in between. We can use measurements to analyze performance. This isn't as easy as it sounds. First, we have to have access to the CPU, and if we're using an advanced processor with a new chip, the chip may not be ready. We need to know the data inputs that give the worst case execution time, and if we're interested, the best case execution time. And we need to be able to make the execution of the program visible so that we can actually measure it. Despite these problems, this is still an important method for performance analysis. We need to understand how to feed data to the program to make it execute the right paths and exercise the right cache behavior so that we can understand its various modes of operation. We need to know the desired input values that give us worst case execution time. We may need to write software scaffolding to generate these input values. And we may also need to use that scaffolding to examine the outputs and generate new inputs in a feedback-driven application. We can use traces of program execution to analyze performance. A trace is generated by instrumenting the program in a way that it saves information about the execution paths of the program. There are a variety of tools available to help us instrument programs. This instrumentation does require modifying the program, but we can typically, these changes do require some modification to the executable program. The trace files generated are large, but given that disks are large and inexpensive today, that's not as big a problem as it used to be. Traces are widely used for cache analysis. They can also be used for some other aspects of performance analysis. We can physically measure performance using techniques such as in-circuit emulators or logic analyzers. In the case of a logic analyzer, we need to be able to see events on pins. This can be particularly important for real-world physical measurement can be particularly important for real-world input streams in which it's difficult to generate realistic data, and the only way to exercise the system on real data is to plug it in. CPU simulation is another very important technique that's widely used. Simulators vary in their accuracy. Some are instruction level accurate, some are less accurate and may not capture some aspects such as all the details of performance or details of power consumption. Cycle accurate simulators provide accurate clock cycle timing for the execution of instruction. This requires the simulator model the internals of the CPU, which means in turn that the creator of the simulator needs to know how the CPU works. Some aspects of the CPU's operation may not be publicly available. Simple Scaler is a widely used CPU simulator. Here is a test program we use to simulate the execution time of our FIR filter using Simple Scaler. The inner loop of this code is the FIR filter itself. The outer loop executes the FIR filter several times repeatedly. That's required in order to help us take into account the overhead associated with running the simulator. So you can see in the table that we've run the FIR filter for different numbers of iterations. As the count of the number of runs of the simulator increases, the apparent execution time of the FIR filter decreases. That's because we're amortizing that overhead over more executions of the FIR filter. A variety of optimizations can be used to improve code performance. Loops consume much of the execution time in many programs, and they're a good target for optimization. Some simple loop optimizations include code motion, that is, moving code outside of the loop body that doesn't need to be there, induction variable elimination, which we'll talk about in more detail in a minute, and strength reduction, for example, replacing an integer multiplied by 2 with a shift. Here's an example of code motion. In this unoptimized loop, we compute n times n during each iteration in order to test the loop. But we don't need to change. But since n and m don't change inside the loop, we can compute it once in the preamble to the loop and then simply use that value during execution. The induction variable is the loop index. So consider this nested loop with one loop inside the other. In order to access these two-dimensional arrays, we need to do a multiply and addition. But notice that the left-hand side and the right-hand side of the assignment use the same offset inside the loop, ij. That entails a calculation of I times m plus j. We don't need to repeat that calculation. We can compute it once and share it. We can also increment that value at the end of the loop body rather than re-perform the multiplication on every iteration. A loop nest, as we saw, is a set of loops, one inside the other. If we don't have any conditionals inside the nest, we call it a perfect loop nest. Loop nests are more complicated to analyze, and one of the aspects of analysis that becomes more complex is cache behavior. Because loops use large quantities of data, cache conflicts are common and important to understand. Because arrays are often large, we can find cache conflicts that may not be obvious. Here's an example of a conflict between two different arrays in the cache. The A array starts at location 1024. The B array starts at location 4099. If we look at the mapping of A into the cache and B into the cache, we'll see that the 0th elements, for example, map into different parts of the same line. So if we access A and then B and then A again, the B reference will have knocked out the early parts of A from the cache, which means that our prefetching of the first few values of the A array has not been saved, and we need to refetch. That costs us execution time. Array padding is a simple technique we can use to change how arrays fall into the cache. Consider this array, which has the right-hand index over 3 different values. So the number of elements in the right-hand index of the array don't match well with the number of elements that can be held in one cache line. Let's pad the array with extra elements. Now all the 0, 0, 0, 1, 0, 2 fall into one cache line, and the next cache line includes A1, 0, A11, A12. We now have a much cleaner relationship between array elements and cache lines. Loop tiling is an important way to optimize caches. Loop tiling adds loops in order to change the way we iterate through the arrays. In the case of the left-hand side loop, we take a given value of x sub I and we operate on it with every value of the y array. This may be inefficient use of the cache for the y array. On the right-hand side loop, we've added an extra loop with a new induction variable so that we can use a small number of x values and compute with them a small number of y values. So we bring those y values into the cache once, we use them several times, and then we go on to the next element. Performance optimization is both a science and an art. There are some hints that will help us improve the execution time of our programs. We want to use registers efficiently. If we have inefficient use of registers, that means we're reading and writing memory more often. We want to use page mode memory accesses where possible. This is a feature of memory components that allows us to reduce the time it takes to compute addresses inside the memory. We also want to analyze cache behavior carefully. Instruction conflicts can be handled by rewriting code and possibly rescheduling. Conflicting scalar data can be moved. Conflicting array data can be moved or padded. Power consumption is another important metric for embedded systems. The analysis we need for power optimization is similar to many aspects of performance optimization. Energy and power optimization is a critical concern in many embedded systems. Remember that energy is the ability to do work. It's clearly important in battery-powered systems, which can provide only a limited amount of energy before the battery dies. Power is energy per unit time. This is important in battery-powered systems, but it's also important in systems plugged into the wall because that power becomes heat, and many modern computing systems are limited by their heat dissipation. We can measure energy consumption using a hardware setup. If we want to measure the energy consumption of the A function, for example, we write a program in which a loop continuously calls A. We then use an ammeter through the CPU to measure the current flowing through that CPU. That indicates the amount of current used to execute that function, of course with the overhead of the loop. There are several sources of energy consumption in a complex computing system. Typically, memory transfers are an important aspect of energy consumption. If we look at the larger system, for example in a cell phone, we find that even the execution of the program's energy may be dwarfed by factors such as the energy consumed to run the screen or to run the radio. Cache behavior is important to energy consumption, and we can see a very interesting phenomenon in the case of energy. If the cache is too small, then the program thrashes. We bring locations into and out of the cache constantly. Clearly, this burns energy. But if the cache is too large, that consumes excessive power as well, because the power consumption of the cache is a function of its size. Making the cache larger than it needs to be wastes power. We can see that in these graphs. The top graph is energy as a function of the size of the instruction cache and the data cache. And we can see the execution time in the bottom chart as a function of instruction cache and data cache. If we look at the execution time chart on the bottom, we see that for very small instruction caches, we have very large execution times. That's because we don't have enough cache to hold the instructions for the loop. But if we look at the energy plot on top, we see that for very small instruction caches, we burn a lot of energy. We increase the cache size a little, and we hit our sweet spot. But then we increase the cache size more and we start to burn more energy because of the overhead associated with using a larger cache. Once again, we can come up with some heuristics to help us optimize programs for energy and performance. To a first order, high performance equals low energy. There are some trade-offs that require us to slow down the program in order to reduce energy consumption, but in many cases, high performance also means not wasting operations, which in turn means low energy. Once again, we want to use registers efficiently. We want to identify and eliminate cache conflicts. Some moderate amount of loop unrolling eliminates some of the execution overhead of loops. We can eliminate pipeline stalls, and inlining procedures may help, although in some cases it may increase cache thrashing. For efficient loops, we have some heuristics once again. Don't use function calls inside the loop body. Keep the loop body small to enable local repeat instructions if we have those kind of instructions on our processor. We often want to use unsigned integers for loop counters. We often want to use a particular test for the loop counter. Some compilers, for example, prefer that we use a less than or equal to. And we can make use of compiler global optimizations in software pipelining. Here's an example of a single instruction repeat from the TI C55X processor. We can see this is a very efficient loop, which is enabled by the block repeat operation of this DSP. But in order for the compiler to find it, we may need to code our high-level language program in a proper way. Program size is also an important metric for some program size is also an important metric for some embedded systems. We want to reduce the hardware cost of memory. We may also want to reduce the power consumption of the memory units. We can optimize for program size in both data and instructions. Data size minimization, for example, means we're using constants, variables, and data buffers rather than declaring new ones in each part of the program. In some extreme cases, we may use instructions to generate data rather than by storing data directly in memory, although we typically do that only for very small processors. We can avoid function inlining to reduce code size. We can choose a CPU whose instruction set gives us compact instructions. And we can make use of the instruction set specialized instructions wherever possible. To summarize, embedded systems must meet deadlines, and worst case execution time, or WCET, is a critical metric used to evaluate deadline behavior. We can analyze programs using several different techniques. We can also optimize programs to improve their performance. Power consumption is another important aspect, and that analysis is related to what we need to do for performance analysis.